statistics, and we're going to look at the next type of inferential statistics, and that's known as hypothesis testing. And we're going to originally first look at dealing with one sample, and then we're going to look at two samples. All right, so let's look at some terms. A hypothesis is a claim or a statement about a population. A hypothesis test is a procedure for testing a claim about a population parameter. I think I've got the word a claim a couple too many times, but it's a procedure for testing a claim about a population parameter. There's two types of hypotheses. The null hypothesis, which is a statement about a population that includes equality. It's denoted either by an H0 or an H sub 0 with an H0 at the bottom. And then the alternate hypothesis is a statement about a population that does not include equality, which is denoted H sub A or H1. Now, let me talk about terms. Terms that include equality are terms that include the equal sign, the less than or equal to sign, or the greater than or equal to sign. And statements that do not include equality are statements that include the less than sign, the greater than sign, or the not equal to sign. The null and alternative hypotheses need to be complements of each other. It's computed from that sample data, and that's used to make a decision on whether or not to reject the null hypothesis. We have critical or rejection regions, and it's a set of values of the statistics that would cause us to reject the null hypothesis. The critical value approach is a very old-fashioned approach. It's discussed a little bit in your book, but really most statistical software now do not use the critical value approach. And so I'm going to just explain it, but we're not going to be doing it. We're going to be doing what's known as using a significance level and the p-value approach. So the significance level is denoted by an alpha. Now remember, we had in confidence levels were 1 minus alpha, and they were things like 99, 95, and 90. And alpha are numbers like 5%, 10%, 1%. And critical values separate the critical region from the rest. Okay, now we have the tails, and we can have three types of tests. We have a two-tailed test. That's when the alternative hypothesis includes the not equal to symbol. A left-tail test, when the alternative hypothesis has the strictly less than symbol. And a right-tail test, when the alternative hypothesis uses the greater than symbol. So two-tailed is not equal to. Left-tail is when the alternative is less than, and the right-tail is when the alternative is greater than. Note, tails are usually considered when calculating hypothesis tests by hand. Extreme or more extreme is the one representing the sample data, assuming the null hypothesis is true. I've never thought that definition makes sense to students, so I made up my own. It is, in other words, the probability that the null hypothesis is true. So in other words, if the p-value is small, then we're going to assume that the probability that the null hypothesis is true is very small, thus it must not be true. Let me say that one more time. If the p-value is small, and the p-value is the probability that the null hypothesis is true, is very small, then we can assume the null hypothesis must not be true. All right, so the traditional or critical value approach, remember I told you, is very old-fashioned, and you find a test statistic that falls in the rejection region. You have to do this approach by hand. Minitab, no statistical software does this approach. It's very old-fashioned. All statistical softwares, SPSS, Minitab, many of them use the more modern approach, which is the p-value approach. And the p-value approach, Minitab, the statistical software, will find the p-value for you. And if the p-value is less than or equal to the significance level alpha, then we reject the null hypothesis. If the p-value is greater than alpha, then we fail to reject the null hypothesis. Now remember, the p-value is the probability that the null hypothesis is true. So if it's small enough, and what's small enough? Small enough is smaller than the significance level. Then we say it must be that the null hypothesis is not true. So we reject it. Notice we never say except the null hypothesis. We either reject it or we fail to reject it. If we're dealing with confidence intervals, we do the same thing, but we reject a claim that the population parameter has a value that's not included in the confidence interval. So we reject the claim that the population parameter has a value not included in the confidence interval. We do not accept it, nor do we prove it's true. If we reject the null hypothesis when it's true, we have a type 1 error. Alpha is the probability of a type 1 error. That's a probability of making that error, which is bad, but at least we control it. We know what the significance level is. If we fail to reject the null hypothesis when it is false, we have a type 2 error, and we do not have as much control over a type 2 error as we do over a type 1 error. That's why we never say accept or prove the null hypothesis is true, because if we're wrong, it's a probability that we do not control. Confidence intervals for hypothesis tests. Confidence intervals contain the likely values of a population parameter. If the confidence interval contains the claimed value, then we do not reject the null hypothesis. If it does not contain the claimed value, then we reject the null hypothesis. Of hypothesis tests that we're going to look at, just like we did before when we looked at confidence intervals for estimating population proportion, we looked at confidence intervals for estimating the population mean, and we looked at confidence intervals for estimating the population standard deviation or variance. We're going to do the same 3 for hypothesis testing. So in 8.2 we start talking about testing claims about the population proportion P. All right, so the requirements for the population using a testing a claim about a population proportion are very similar to the same requirements we saw when we were doing a confidence interval. It needs to be a simple random sample. The conditions of the binomial distribution need to be satisfied. Independence, only 2 answers, yes or no. The NP and NQ are 5 or more. That's to use that normal approximation, but Minitab version 17 and 18 both do the exact method, so we don't really need this, but it is the way that your book is doing it, so I wanted to make sure that it's discussed. The same place we went for confidence intervals. We enter in the appropriate data, but this time we need to select the appropriate alternative hypothesis. Then you either use the exact method or the normal approximation. Of course, I think the exact method is better because it's the exact method. It gives you the exact answer, not an approximation. So let's look at an example. Suppose we have x is 39, and then n is 39 plus 32, which is 71. Alpha is 0.10. My null hypothesis is equal to 0.5. My alternative hypothesis is the population proportion is greater than 0.5. So we have a right-tail test. If the alternative is greater than, it's known as a right-tail test. If we're using the normal approximation, when we put those values in, we get z equals 0.83. When you use the exact method, there will be no test statistic. The p-value for the normal approximation is 0.203. For the exact method, it's 0.477. The decision, in either case, the decision is the same. P is greater than the significance level of 0.10, so we do not reject the null hypothesis. This is really very rare. It still has the same requirements we saw when we did the one sample Z confidence intervals. Simple random sample, population standard deviation is known, the population is normally distributed, or the sample size is greater than 30. But this is rarely the case that we use a Z-test. So Minitab doesn't even do it. If n is greater than or equal to 30, then a t-test approximates a z-test. So we're going to be getting about the same answer anyway. So Minitab doesn't even do a we don't usually do the one sample Z with testing hypotheses. But we can try. I mean, it's something that we're going to do academically, right? But in real life, it's rare that you would do it. Stat basic, stat 1 sample Z. You enter the appropriate data, go to options, select the appropriate alternative hypothesis, right? Minitab is one of the few that actually does the 1 sample Z. Most statistical software packages don't even. So let's look at entering this data in N is 50. Sample mean is 120. Sample standard deviation is 12. Significance level is 0.05. My null hypothesis is mu is equal to 118. The alternative is mu is greater than 118. Again, we've got another right tail test. So we go, when we put all that information into 1 sample Z, stat basic stat, 1 sample Z, we end up with a test statistic of Z equal to 1.18. The p-value is p equal to 0.119. Since p is greater than 0.05, which was our significance level, we do not reject the null hypothesis. Then we're going to do the same thing we did with confidence interval. We are going to go to the t distribution in the 1 sample t. Stat basic stat 1 sample t, enter the appropriate data, make sure you select the appropriate alternative hypothesis, which matches this mathematical symbol for the alternative hypothesis, which will either be not equal to, greater than, or less than. So let's put the same example in that we just had a minute ago, but this time let's go to t. When you put n, is sometimes Minitab on certain sites, Minitab asks for n sample size, and sometimes it asks for degrees of freedom. In this part, it asks for the sample size, so be careful to check whether Minitab is asking you for degrees of freedom, which would have been 19, or sample size, which is 20. When you go to the alternative hypothesis and put in greater than, then the test statistic, you click OK. The test statistic is t is equal to 0.75. Again, the p-value is larger than our significance level. And again, we got the same conclusion, do not reject the null hypothesis. Or variance. And again, it's very similar to what we saw with the confidence intervals. Distribution is skewed. It uses the chi-square distribution. All values are positive. Uses degrees of freedom and -1. All right. If you put these numbers, this is the height of supermodels, and what we're going to test is there enough evidence to suggest that supermodels vary less in height than women in general? If you look around any classroom that you've ever been, or just in public in general, you see that there's women who are close to 5 foot. There are women out there who are closer to 6 foot. Women in general vary a great deal, but supermodels all are pretty tall. And so the hypothesis is that there is less variability among supermodel heights than there are in the heights of women in general. So they took a sample of these supermodels' height, and so put them into a column, and then go to stat basic stat 1 variance. When you enter the values from a column this time, and you're going to get that the p-value is 0, which means we reject the null hypothesis. There is enough evidence to suggest that supermodel heights vary less than the normal population. Remember, if the alternative is less, and you need to change the alternative on the option page to less than, which makes this a left tail test. We are starting to get into a little deeper material here in this class, so I think it's a good idea to go back. You should have read the chapter 8 from the textbook, listen to the lecture. I would go back and read it one more time now that you kind of listened to my lecture. Then go do the assignments on the MyMathLab website. There should be some problems picked for 8.1, 8.2, 8.3, and 8.4. Then watch the lecture recording for Minitab Lab 8. And when you're done with that, then do Minitab Lab 8. And of course, save your answers, as I have always asked you to, as either a Word document or scan it as a PDF file, and then upload it to coursework on the portal. There'll be a place for you to do that when it's due. All right, thank you very much, and let me know if you have any questions.